So, welcome to the session 9 on the course machine learning. The topic under this particular session is estimating means of K Gaussian using EM algorithm. So, myself Naveen Mukkapati, assistant professor in computer science department. Coming to the aim of this particular session, to familiarize the students with concept of estimating means of K Gaussians using EM algorithm. And the instructional objectives of this session are discuss the Gaussian distributions and discuss the estimating means of K Gaussians using EM algorithm. And the learning outcome of this particular session is at the end of this session, so student will able to describe the Gaussian distribution, and they are also able to describe the estimating means of K Gaussians using EM algorithm. And coming to the why we need to go with the Gaussian distributions. So we know that in most of the cases, whatever the data we are having, the data must be in one dimensional or two dimensional or higher dimensions, and these dimensional data must follows the Gaussian distribution or normal distribution. So here this assumption is used by most of the researchers and scientists to model and analyze the many of different applications. And most of the cases we are going with these distributions only, and the advantage of this Gaussian distribution is it's very closer to the natural distribution of our data, and most of the natural phenomena such as height of population, blood pressure, shoe size, exam performances, and many of follow this particular distribution. It means that with the help of this particular distribution we simply model the these natural phenomena data. Okay, and if you follow this particular data, then it's very easy to do mathematical operations. It's one of the important thing. So if you want to apply the mathematical operations on the data, then we need to model our data as the Gaussian distribution or normal distributions. Okay. So this is the reasons why we need to go for the Gaussian distribution. So here this particular diagram is indicating representing our data in the Gaussian distribution form. So here x-axis indicating our data instances, and y-axis indicating the probability density function or Gaussian function. So here this value is the mean value. We are denoting that one as the mu, and this Gaussian distribution is follows the 99, 95, 68 rule. So it means that mu plus sigma or mu minus sigma. So under this the total 68% of instances are covered, and mu plus 2 sigma and mu minus 2 sigma. Under this particular range, total 95% of data is covered, and at last mu plus 3 sigma and mu minus 3 sigma. Here the sigma is the variance. So here within this particular range, total 99% of data is covered. So here whatever the data we are having, that particular data is simply follows either normal distribution or Gaussian distribution. So if it follows the Gaussian distribution, then data must be sorry, 1 minute, data must be distributed as like this. Okay, so this mu is indicating mean, and this sigma is indicating the variance. Okay, so on the x-axis we are taking the data instances, and the y-axis we are taking the probability density function, or this is a Gaussian distribution function. Okay, so here whatever the values we have after mu plus 3 sigma and mu minus 3 sigma, they are treated as the outliers. Okay, so here this Gaussian distribution function or Gaussian distribution of data is mainly used for identifying the outliers, and it's also very much useful to do most of the mathematical operations on this particular represented data. Okay. And coming to the formulas which are used for our probability density function and mean estimation and variance estimation. So here this is the formula for probability density function. Actually we are saying it's a Gaussian distribution function. Probability of x mu comma sigma square. Here mu is the mean and sigma square is the variance estimation. Okay, so the formula is 1 by square root of 2 pi sigma exponential of minus x minus mu whole square by 2 sigma square. So here the pi value is a well known constant, that is the 3.14, and here this entire thing is giving a probability density function. We are saying it's the Gaussian distribution function, and here this one is depends upon our data instances x and mean of our sample data and variance of our sample data, and these are the formulas for finding the mean estimation and variance estimation. So mean formula is sigma xi by m, and variance formula is sigma xi minus mu whole square by m. Okay, so here these two values are calculated with the help of available sample data. So after calculating these mean estimations and variance estimation, so we simply find out the probability density function. So coming to the estimate means of k Gaussians. So here how we are estimating the means of k Gaussians? If we have the k number of Gaussian distributions, then how we are calculating the means of these k Gaussians? Okay, so generally this particular method is used to generate the data. So it means that if we have the missing data or noises, or if we have latent variables, then to generate that particular data we simply go with this approach. So here we assume the data as capital D, and this is drawn from the mixture of k distinct normal distributions. Why we need to consider the k distinct normal distributions means here we are estimating the mean of k Gaussians. So we are considering there are k distinct normal distributions of our data. So the total data is denoted as D. This data is generated or formed by the mixture of k distinct normal distributions. Okay, so here this one follows the two main steps. So one of the step is identifying randomly one of the distributions among the k distributions. So and coming to the second step, in the second step we simply take a single random instance xi, so which is generated according to the selected distribution. So it means that whatever the distribution we selected in the first step, so with the help of that selected distribution, so here randomly we are generating an instance xi. Okay, so this is the two-step process which is used to generate our samples. So here this is the diagrammatical representation of our k Gaussian estimate means of k Gaussians. So here we are considering k value as the 2. It means the two distributions we are having. This is one of the distribution and this is second distribution. So on the x-axis we are considering our instances. On the y-axis we are taking our Gaussian function or probability density function p of x. So here if we consider these instances may be generated by this Gaussian distribution function, or it may be generated by this particular Gaussian distribution function. So just now only we discussed that here this is having two steps in the process. So in the first step we are randomly picking one of the Gaussian distribution, and after picking that we simply generate one of the instance. Okay, so this is the diagrammatical representation of two Gaussian distributions. So here how we are randomly picking these distributions? Is there any probability value to picking one of the distribution means? So in case of a single normal distribution is chosen with uniform probability, it means that we are having equal probability value to pick the one of the distribution among the k Gaussian distributions. Okay, so here each of k normal distributions has the same known variance. Okay, so we know that for our Gaussian distributions we require the mean value mu and variance sigma square. Okay, so here mu is unknown value here, but our variance value is the known value, and this variance is equal for each and every distribution. If we have n number of normal distributions or Gaussian distributions, then n number of distributions are having the same variance. Okay, but mean of those distributions need to be identified at here. Okay, so here our aim is identifying the mean of those distributions. Okay, so here we are learning the learning task is to output a hypothesis, that is h is equal to tuple of mu1 mu2 up to mu k. So here we are considering